Hello everyone. In today's video, we shall see the basics of kinematics, particularly the equations of motion and translating graphs, particularly position time graph, velocity time graph, and acceleration time graphs. The students often get confused like how to translate these into the different graphs. So let me explain with the help of a simulation from O physics. So this is a simulation in which you can see the acceleration versus velocity versus time and position versus time in different colors. So let me uncheck these boxes and start from the beginning, the basic, in which there is no change in the acceleration. So there is no change in the acceleration, right? Acceleration is made to zero. So now let us check velocity time graph. And the basic of this is the acceleration is defined as the rate of change of velocity, meaning if you have velocity versus time graph, the gradient of this velocity versus time graph is giving you acceleration, right? So let us check this on. You can see here, the initial velocity is already set up here, but you can still move it. There is no change in the velocity, meaning as long as there is no change in the velocity, the gradient is zero. Because the gradient gives you acceleration, acceleration is zero. Let me make it to the other position. Look at this. Even now, the acceleration remains zero. Zero and zero. Yeah. Now let us click on the position versus time graph. When I click on the position versus time graph, it is also showing it's parallel to the time axis, which indicates that there is no change in the position. So no change in the position. As long as there is no change in the position, with respect to time, there is no velocity. Once again, the gradient of position versus time graph gives you velocity. The gradient of position time graph gives you velocity because it's a rate of change of position. So velocity is defined as rate of change of position. It is nothing but gradient, right? So this is y2 minus y1, which is change in y-axis values over x-axis, which is nothing but the gradient. Similarly here, velocity versus time. So the gradient of display position versus time graph is giving me velocity as long as there is no change in the gradient. That means as long as the gradient value is zero, the velocity value is also zero. Now let us check the other one in which I'm now going to change the acceleration to some positive value. So what we understand here, this acceleration is constant and acceleration is positive. Let me write here, acceleration is constant or uniform, and it is also positive because it is along positive y-axis, right? Now let me click on the velocity versus time graph and see what would happen. Look at this. This is a linear graph, which indicates that the gradient is constant. Look at the gradient. If I take the gradient of these two, between these 2 points, the gradient is same. And the gradient is same everywhere. So as long as it has a constant gradient, that means it has a positive velocity. Now let me take this down, which is a negative acceleration. See what would happen. Look at this. I'm taking it to the negative acceleration, which means the acceleration is constant and negative. So in the velocity time graph, the negative gradient will give you a negative value of acceleration. That means in case you have acceleration versus time graph given like this, and you are asked to translate this to velocity time graph, you will have to keep two things in mind. Number one, acceleration is constant. That means the velocity versus time graph must be linear. And this is negative, which shows that it has negative gradient. That means It should be like this. Now let me check on the position versus time graph of the same. Look at the position versus time graph. You can just take it to 0. This is how the position versus time graph looks like. Here, you may think like, how can I translate this graph to this graph now? All right. So let us go back to the previous one. Again, we make use of the same thing, that is gradient. So I'm redrawing the positive acceleration versus time graph. So let me take it as positive. Now check velocity versus time graph. It is straight, which shows that the gradient is constant. Acceleration is same. Now look at the position versus time graph. So position versus time graph is exponential, or it's like a parabolic in shape. Now imagine I'm asked to draw velocity versus time graph and position versus time graph is given. All I need to do is check the gradients. Look at this. Initially, the gradient of position versus time graph is 0. The velocity is 0. Now I'm selecting some point somewhere here and draw the gradient. So I can see that compared to this gradient is maximum, and also it is positive gradient. So somewhere here, and again here, the velocity still increased, and it has more gradient as it goes up. So we can also check this position versus time graph, not from 0, but somewhere here. All right, let me just go back to acceleration, positive acceleration. But now look at this. So this is something in a parabolic shape, which is like holding some water. Now, if you check this, again, acceleration is constant, but velocity is not starting from 0. If you look at this, it exactly fits in the equation v is equal to u plus at, correct? So initial velocity is not 0, it has some velocity. And acceleration is the gradient of this particular graph. Yeah, and t for time. Now, when you look at this as y is equal to mx plus c, compare this with y is equal to mx plus c, see it exactly, you know, in according to this equation, wherein you see along x-axis there is time, x-axis there is time, y-axis there is final velocity or velocity, and y-intercept is initial velocity u, and the gradient is the acceleration. When you calculate the gradient of this velocity time graph, you would get acceleration. So v is equal to u plus at is the equation for this. But what about this equation? So when you look at the position versus time graph, you know this displacement is defined as the change in the position. From the Suvat equations, we write S as ut plus 1 by 2 at squared. Now the displacement is the change in the position. So let us say x minus x naught is, this is the initial position and this is the final position. Sorry, this is final and this is initial. Initial velocity plus half at squared. Now x will be x naught plus ut plus 1 by 2 at square. This is exactly in accordance with this parabolic equation. If you have any questions in that, you can put in the GeoGebra the values and check for this parabolic curve. Graphs are most important. Whenever you have acceleration versus time graph, which is uniform acceleration versus time graph, position time graph looks like this. And obviously velocity time graph is linear. This is an important thing. Now, let me take this to the negative axis again, the same thing. Now I am checking on this too. Look at this. It is again along negative axis. Look at this, right? Not the ball which is dropped downward. Now they ask you to draw the position versus time graph. Now the graph exactly looks like this, because if you take this particular as your reference line, now this is positive y-axis, this is negative y-axis, positive x-axis, negative x-axis. So when you define the positions, now look at this. Acceleration is downward along negative y-axis, which is negative g. That means this is negative side and it's a constant. A is equal to minus g. It's going to be 0 in the beginning because initially it is 0. Look at this. And then what happens to the velocity? It keep increases as it falls down. So the velocity keeps increasing, and as it's uniformly accelerated body, because g is on the surface of the earth is always like close to 9.81 meter per second squared. So you can see that there is a constant increase in the velocity in the downward direction. So velocity is also along the negative direction. So you can see that velocity is increasing along the negative axis. All right. Now let's see. And again, the position time graph in the same way. Let's say you can just take this position to 0 as well. If I take this as a reference line. Now, when I bring this position to 0, you can see this. There is an exponential increase in the position, but in the negative direction. Again, the position is taken along a negative y direction. That's why you can see in the negative y-axis, right? So this is the translation, how we can take acceleration versus time graph to velocity versus time graph and the position versus time graph. So in the same example, if I take that there is this ball is hitting the ground at a particular position and rising up, all right? Now what would happen to the acceleration? Acceleration is anyways be the negative g, but here the ball is hitting the object. I cannot show this on the simulation, but I'll show you here. So as it hits the ground and rises up, the velocity versus time graph initially starts with 0. This is the position of the ball in the beginning, and the velocity increases in the negative direction. And in no time, the ball rises up. That means the ball is now moved towards the positive y-axis. That means positive value of. And now the velocity keeps decreasing. Am I correct? This is how the graph look like. This is velocity time graph of the ball, which is falling from a height. After bouncing, it just goes to a certain height, because you can't expect the ball to raise to the same level, considering it is offering some friction. Now, if you look at this position, the ball again came to rest. Here the velocity is 0, but you can see that this is the maximum height the ball reached after the first bounce. This can be taken as a question. Let's say these are the various positions in velocity time graph, A, B, C, D, E, and the question is of the which position of the graph indicates the maximum height reached after the first bounce. So all you need to understand is this is the path taken by the ball while coming down. And as it reverses the direction, the velocity is also reverses because it's a vector quantity. And again, from here, the velocity is decreasing and stopping here. Whenever the final velocity of the ball is zero, that means it reached the maximum height. That means the answer for this question is E. The letter E indicates the position of where the ball reaches the maximum height after the first bounce. This is how we can translate the various graphs. Now let us check one more important thing. I'm just trying to move the acceleration like this. Now check the velocity versus time graph. So you can see that the acceleration is positive from here to here. Yes. And acceleration is negative from here to here. That means the velocity versus time graph must have positive gradient and also the negative gradient. Let's see whether it happens in velocity versus time graph. Look at this. This particular part from here to here is showing us the positive gradient. From here to here is showing us the negative gradient. The position time graph for this particular graph. So here again, you can see that the velocity is constant. The velocity is increasing, the positive gradient, and the velocity is decreasing. So let us translate to the position time graph. Look at this. So here you can see that the velocity is increasing. Now focus only on these two graphs. Now check this out. Now, how do we translate position time graph to the velocity time graph? Draw the gradients. Initially, the gradient is 0, so velocity is 0. Now select one point, see the gradient. It's more. Look exactly here. The point from here to here indicates that it has increasing gradient. So velocity is increased from here to here. Now look at from this part to this part, which is from this part to this part. You can see that the gradient is now is negative, right? Which indicates that this is decreasing with the negative acceleration. This is the negative acceleration, this part. That means you can just take these two graphs in mind now. Forget about the velocity versus time graph for a moment. Now look at acceleration versus time graph and position versus time graph. Look at this. From here to here, uniform acceleration. This part of this graph gives you uniform acceleration. We have seen that it's like a parabola, upside parabola. Now this is the negative acceleration. That means the body is slowing down. The body slowly slows down and the position is, look at this, the position is, there is no change in the position, right? So this particular part gives you the positive acceleration. This particular graph part will give you the negative acceleration. This is the most important part of this. Now let us try to make it, let us try to have one more, which is like sometimes positive, sometimes zero, and sometimes negative. Check this out. Look at this. From here to here, what's happening is there is no acceleration. That means the position time graph, if you look at, this is almost close to time axis. And after that, acceleration is more. Look at this part. So there is more steeper value, acceleration, position time graph. From here to here, it is negative. From here to here, the position is slowly reducing, and then Here to here, it is 0. It's flat. Yes. Now let us translate this graph to velocity time. Look at the velocity time graph. Here we go. There is no change in velocity from here to here, right? So no acceleration. Look at this. The value of acceleration is positive. So it should have positive gradient. The value of acceleration is negative here, which is negative gradient. There is no acceleration. That means the velocity time graph is flat again. So this is one more important model to show you how do we translate the different types of graphs. Thank you so much.